Hello, hello, sixth grade. Here are your first set of review notes. These review notes are for stars and galaxies. This will be the first video. The second video will be for the sun. So this first part is for our star and galaxy notes. The first part, thinking of the whole universe. Where are we in the universe? And you can think about that in terms of this slide right here. If we start with our solar system, there's our star, the sun. Here's our solar system, there's Earth. Our star, the sun, is part of a whole galaxy of stars called the Milky Way galaxy, and there are billions of stars in this galaxy. Our Milky Way galaxy is actually one galaxy of a few galaxies called our local group. It's a cluster of galaxies, and then the universe itself is made up of billions of clusters of galaxies. So there's so many galaxies, each filled with billions of stars. It kind of blows your mind if you think about how many stars there are in the universe. But what's wacky about that, though, is that all of those things that we see up there only account for 4% of the entire known universe. Most of the universe is dark energy and dark matter, stuff that we can't see, and energy that we're aware that is there, but we've only recently realized that it's there. It's helping to expand the universe. Another cool point, we mentioned this in class, is that because light takes time to travel from stars to our eyes, even though it travels fast, does take time to get there, when you look at a star, you're actually looking at what the star looked like years in the past. If a star is 4 light years away, it means it took 4 years for the light to make it here from Earth to Earth from the star, so that if you look at a star that's 4 light years away, you're actually looking at what it looked like 4 years ago. If it's 1,000 light years away, the star, you're actually looking at the star what it looked like 1,000 years ago. Or perhaps there's a galaxy that is 100 million light years away. You're looking at it what it looked like 100 million years ago. Now, a couple things about understanding how we figured out what the universe is and what it's doing. First is this idea of the Doppler shift. The Doppler shift is, or the Doppler effect as it's sometimes called, is how a person, somebody perceiving something that's giving off waves, how that the waves that the person receives might be different depending if the thing giving off the waves is moving or not. Example of sound is that if there is say a car making a siren, and if it's not moving, that siren will sound the same no matter where you are relative to the car. But if the car is moving, the sound's going to sound different depending if the car is coming towards you and then going away. That's the kind of sound that we talked about at like a race car, where it's higher at the beginning when it's coming towards you, and then it passes you, the sound goes down. It changes the pitch of the sound because it either compresses or spreads apart the waves. Well, the same is true with light. And if something is not moving, it's giving off light and it's not moving, the light will be perceived to be the same on either side. But if it is moving, the light on the side in which it's going towards is more sort of squished together. It causes what's known as a blue shift. Reversely, on the flip side, on the back side, if it's moving away from the observer, it has a red shift. Now, what does that have to do with astronomy? Well, Edward Hubble looked at galaxies and he noticed that they had almost all of them had a red shift, which means that all galaxies are moving away from us. Everything is spreading out. Well, people started thinking, well, if everything's spreading out, let's go back in time. If everything's spreading out, where must have everything started? And that led to this big idea of the Big Bang. The Big Bang theory is that the entire universe exploded out from a single point about 13 billion years ago. It's kind of a mind-blowing idea, but that happened 13 billion years ago. Everything, you, me, every atom in our bodies, every atom in the Earth and in our solar system, the entire universe, boom, exploded out from a single point. That's pretty huge. All right, a couple other things. Oh, how do we know how far a star away is? Well, first thing to think about is the absolute magnitude versus the apparent magnitude, sometimes known as the absolute brightness or apparent brightness. The absolute magnitude of a star is how much light the star is actually giving off. How much energy is it actually giving off? The apparent magnitude or apparent brightness is how much light energy we see on Earth. A classic example of that is the sun. The sun has a kind of average absolute magnitude. The sun only gives off an average amount of light compared to other stars. But my goodness, because it's so close to us, its apparent magnitude is super bright. Look how bright it is out there. That's all from one star, but that's because it's so close. We can think about this with stars as well. We can, understanding the size of stars, we can figure out their absolute magnitudes. We can see or understand how much light the star is actually giving off, yet their apparent magnitude might be different for us observing them on Earth. And because of that difference, we can figure out how far away the star is. For example, if two stars that we know have the same absolute magnitude, yet one star appears to be less bright, it must be farther away because that light gets weaker and weaker by the time it hits Earth. Reversely, if we know that two stars have, or I'm sorry, if one star has a greater absolute magnitude, it's giving off more light energy than this star, yet they appear to be the same here on Earth. They have the same apparent magnitude. It must mean that that higher absolute magnitude star must be farther away in order for their lights to seem the same on Earth. That's one way to figure out how far stars are away. Another way is parallax. Now, parallax was this with the thumb and the two eyes. And objects that are closer, when you move your eyes like this, have a larger parallax. They move farther apart. Objects that are farther away, if you put your thumb way out there, they have a smaller parallax. And so by comparing some stars to stars that are, or even galaxies that are far, far away, you can figure out which stars have a greater parallax. In this example, star A would have a greater parallax than star B when observed from the Earth at two different times during the year. Last little part in here, different types of galaxies. You'll need to know three types of galaxies. One is elliptical, shaped like an ellipse. Another is irregular shape. And the last, my favorite, the spiral galaxy, has big arms that come out of it. And our galaxy, the Milky Way, is the spiral galaxy. And the sun is sort of halfway. It's on one of the arms, kind of in the side there. All right, that's the first part. And I'll just quickly go through these, the different pictures, different galaxy types, all sorts of neat pictures of stars. But now we'll get into the HR diagram. Now, I'm not going to go over this page directly. You can read this through. But really what this page is talking about is this, the great old HR diagram, the Hertzsprung-Russell diagram. And this shows that for the most part, stars that are on the cooler side, so on this side of the diagram, have a lower absolute magnitude. The cooler they are, the less light they give off. That makes sense. And then the warmer they are over here to this side over here, super hot stars, have a higher absolute magnitude. And most stars fit that pattern. They fit that kind of relationship, and those are called main sequence stars. Yet, there are two rule breakers. There are some stars that are cool. They have a low, relatively speaking, they have a low surface temperature, yet they give off lots of light. Why is that? Because they're huge. Supergiants. They're gigantically huge, relatively cool stars, give off lots of light. There are other types of stars that are pretty hot. Some of them get really, really hot, yet they don't give off a lot of light. And those are the white dwarfs. They're small, because they're so small. Even though they're hot, they don't give off a lot of light. Understanding this relationship, we have something called the spectral type that tells you the color of stars, the temperature range, and their relative size, giants, main sequence, or dwarfs. And using this pattern, and you'll need to know this for the test, you can figure out the color, size, and temperature of a star. For example, I'm not going to go through all of these, but for the sun, our spectral type is G2 Roman numeral 5. Well, the Roman numeral 5 can tell us that it's a main sequence star. Roman numeral 5, main sequence star. The G tells us that it's a yellow-white star, so its temperature range is between 5,000 and 6,000 degrees. And the 2 tells us that it's on the higher side of that range. If you look over here, see the lower the number is, the hotter of the range the star is. The higher the number is, the cooler it is. So practice doing some of those color, size, and temperatures. That would be great. All right. The last part of these notes have to do with the life cycle of stars. Now, the life cycle of stars depends on two forces that are fighting each other. The first is fusion pressure. The inside of a star, there's nuclear fusion going around, which is making the star explode out. We call that force fusion pressure, pushing it out. There's also gravity, the great coming in force, the pulling in force of the universe. And so stars are going through this sort of balance or battle of fusion pressure making them want to get bigger, gravity pulling them in. Now, most of the time in a star's life, those two forces are equal, which means the star stays about the same size. Everything is balanced. The star seems pretty happy. Our sun, right now, the fusion pressure of our sun is making it go out, but the gravity's pulling it in, and it's just living a nice, happy life. But eventually that'll change. What will happen for an average size star like our sun is that Eventually, fusion pressure increases and the star gets bigger and bigger and bigger, and it becomes a giant. But then, once it loses some of its fuel and it can't explode anymore so much, it will shrink back down, gravity takes over, it shrinks, becomes a white dwarf, and it's small and hot, and eventually it might turn into a brown dwarf, kind of like a candle that goes out. In that process, it does release some material that can create another nebula, which we'll talk about in a second. Reversely, sometimes really big stars, they kind of start out the same, but when they expand, they become a supergiant, really big. Now, when a supergiant, after it's really big, collapses back in, once it loses its fuel, it falls back in, but the bigger they are, the harder they fall. When they fall back in, they create a supernova, which releases all this energy and material all out. A supernova can turn into a neutron star and perhaps even a black hole. A black hole is an object that is so dense that the gravity is so strong that it pulls in everything, including light. That's the possibility after a supernova. So, look over this page very closely. This shows the two different types of lives of stars. They both start off as nebulas. They both become protostars that then turn into real stars once nuclear fusion starts. They become main sequence stars, perhaps big main sequence stars. One becomes a giant, the other becomes a supergiant. The giant shrinks, becomes a white dwarf. The supergiant collapses violently, releases a supernova, becomes a neutron star, and perhaps even becomes a black hole. All right, the rest of our slides are pictures of these things, which you can look over later. But that's it for our first set of review. Again, as always, if you have any questions, let me know, and we will go from there. All right, take care. Bye.